Okay, hi everybody. Well, my name's Pete Hopton. I'm the founder of Isotope, but I spend a lot of my time contracted to the European Commission as part of the European exascale project called EuroEXA that I'm going to be talking to you guys about today, where I'm the dissemination and exploitation lead. People call me the cooling guy. If you type in thecoolingguy.me, you'll get my LinkedIn profile. Please feel free to type that in and connect to me and send me any questions you might have afterwards on LinkedIn. So, first of all, to introduce EuroEXA, I call this my 100 million euro slide because when you sum up everything on the slide, there's about 100 million euros there. EuroEXA was formed as a result of a competitive exercise organised by the European Commission, and there were 3 Horizon 2020 projects that fed in, each of about 8 million euros, and then around 50 million euros of IP was donated to the project from commercial partners, which meant that the project got in total about 100 million euros of value after it got a further 20 million euros off the European Commission. It's called EuroEXA. It started in 2017 in September and it runs for 3.5 years. And the objective of the project is to take us to a demonstrator of equipment that could be eventually turned into an exascale machine. In terms of that competitive exercise, a number of partners were selected, and this is my NASCAR banner slide that shows you the partners that both selected and supported the EuroEXA project. We've got commercial partners in the form of some large companies and SMEs throughout Europe, a large number of academic partners where there's a substantial amount of IP and experience throughout engineering teams across hardware and software, and a number of significant supporters on the right hand side there. And EuroEXA is what we call a co-design project, so it's not siloed within hardware or software or facility, but it's considering the entire piece and how we can further optimize the delivery of a service, and that service being high performance computing. I'm going to talk a little bit about the underlying problem associated with EuroEXA that we're trying to solve. Let's call this the why. So, who in the room has heard of Moore's law? Let's see everybody's hand. I'm sure there's no one in the room who hasn't. Who in the room has heard of Kuhme's law? We've got a few. And how about Shannon and Hartley? So I like to think that's the only real law on the screen there. And it's the only one that's not called a law. Moore, of course, made the observation that every 18 months or so there was a doubling in the number of integrated transistors on an integrated circuit. Dr. Kuhme made the observation that approximately every 18 months or so, the energy efficiency of compute doubled. So the amount of computing you got from a unit of energy doubled. And Shannon Hartley, from Bell Labs in 1928 and 1948, predating all of this, talked about the amount of power, signal power, to transmit data down a channel. But this can be turned as an equation to describe instead the minimum amount of energy required to transmit a bit of data over such a channel. And that is a ceiling, it's static. And what we're seeing is where Moore's law and Kuhme's law are running into Shannon and Hartley. And you've probably, if you've been in some of the other talks throughout the summit, you might have heard people talking about networking and interconnect being a substantial portion of their future electricity draw. You might have heard about the end of Moore's law as it's dramatized. Actually, the amount of processing and data coming out the chip is increasing, but the energy being used in transmission of that data in the SerDes is hit a ceiling. And this is quite well illustrated by this slide from the University of Manchester, where we have up the left axis, we have energy, and the horizontal axis is distance. And what you can see in red is 2018 and blue 2008. So over here where can you see my cursor? Over here where we're on the chip and we're processing the data, we've got a nice improvement over the last 10 years, of a 10x improvement in the amount of energy versus the amount of data. But if we move a little bit off the package, over the last 10 years, we've got 0 improvement on the copper transmission. So there's a fixed amount of energy for transmitting that data over those copper links. We move over to the right-hand side of the slide, and we've got optical transmission, and there's an improvement in optical transmission, but it's no way near as significant an improvement as the improvement in the energy efficiency relating to that data that's produced. So as a general trend, what we're seeing now is the energy from the processing of the data is small in comparison to the energy, the transmission of that data to memory, network cards, other chips, storage, internodal travel. And that is the limiting factor at the moment. So to make a supercomputer that is at exascale, which is 1 exaflop or equivalent, we've got to consider how we're going to reduce that energy consumed through interconnect and chip to memory, chip to chip. And that requires an increase in density. There's also another factor there, and that's latency. Because in an exascale supercomputer, latency is very significant because you've got all the nodes working together. And so you need to think about the maximum distance from one side of the computer to the other. And that distance, obviously associated with the speed of light and the number of network hops from one side to the other, is going to have an impact upon the computing efficiency of how well all the nodes work together. So the vision is a huge computer made in small boxes, taking up as little space as possible. Well, we've got to try and look at the distance from one side of the computer to the other being small. This is just a little bit of artwork, but if you've ever been to Italy, they like making garages in the ground to put the cars in. So one of the concepts here is 3 stories of containerized data centers into the ground, where we can minimize the distance between server and server in an arrangement that resembles the old Cray 2 supercomputer, except blown up to a bigger scale. And of course, when they made those Cray 2 supercomputers, back then it was transistor logic instead of CMOS. It was made in that shape for exactly the same reason that this one would be made in this shape. So in terms of thinking about 60 megawatts in a 35-meter diameter, and we've got a circle of 10 containers that stack 3 high with a core in the middle. That means that in each container we've got to fit about 2 megawatts of compute. Conceptually for us, that's 2 rows of compute backs to the walls of the container. The maximum width of the container on European roads is 3.2 meters. So we've got to think about the insulation and the delivery of services to those cabinets, and then a service aisle up the middle. And that starts to impact the size of those cabinets. We're putting in a prototype into Daresbury Labs as part of the project, which will be deployed around the middle of next year, become operational. And that features a full-size container with 3 cabinets worth of state-of-the-art compute that I'm going to show you a bit more about in a minute. So in order to fit everything into this container, this 2 megawatt box, we have to turn OpenRack up to 11. And that means we need to start thinking about 100 kilowatt plus cabinets. Now OpenRack for us is perfect for liquid cooling because it reduces the wasted space on the footprint that you'd normally get associated with a 19-inch rack and allows us to maximize density. And maximizing density is a key push for us. And in terms of that, distributed DC power enables the consolidation of the PSUs. We've been working with a Scottish company to maximize the density of those power supplies by liquid cooling them. That's enabled us to look at around 30 kilowatts of power conversion per U. But to fit those 2 rows of cabinets inside of our shipping container, we're going to have to reduce the depth of the cabinet from 1060 to at least 960. But 200 mil of that is the cable zone. So part of the philosophy here is how do we minimize the size of the cable zone while still enabling the connectivity of the system. Now, totally liquid cooling helps enable that because we don't have to think about airflow in the front and airflow out the back. So we can put these cabinets against a wall, and our cables in the front can obscure a large portion of what would conventionally be seen as airflow. When we look at a cabinet where we shorten that cable zone by 100 mil, we've got a 960 deep cabinet where the OCP equipment zone is standard size. And this enables us to fit those 2 rows down that container and still put it on European roads. In terms of the design feature of that cabinet, to achieve the power, we need to look at 3 48-volt bus bars. The power supply is located at the top of the cabinet, and then the coolant manifolds for distribution of cooling fitting between the bars and connecting to each server individually. We've got 32 1OU server boxes, and then a number of liquid-cooled high-speed network switches. An allocation in the middle of the rack for battery storage, where we have to look at batteries that have a very, very fast discharge capability, because the objective here isn't holding this thing up for an extended period of time, it's holding it up for a short period of time in the case of power failure. Now, in terms of looking at the rack design, one of the features, this is an early CGI image of one of the racks. One of the features we have here is where at the front the network cables come out sideways. That's because by the time you think about those QSFP cages coming out the front, and then the connector, and then the cable bend, that's our 200 mil cable zone gone. But by having them come out sideways, we're able to avoid that problem. And then inside of that, we have 16 ComExpress extended motherboards, each with an AUX 12 volt. ComExpress is an open form factor of motherboard, which comes as a daughterboard configuration. So I'd suggest people look at ComExpress Extended, which they're trying to push into the server market if they're more interested in looking at that. And at the rear, we have heat exchangers and pumps. To look at how that looks with our final IT, we have 16 devices as such, each one with a processor, an accelerator, and a number of sticks of RAM, and then some Firefly connectors for high-speed interconnect. And one of the circuit boards that fits underneath them that comes out the front has a high-speed network switch on. So we've got 16 200-watt boards, maybe even a little higher than 200 watts inside this unit, and a high-speed network switch, with then QSFPs coming out the front with 8 by 100 gig for uplink. This little device on the front here is known as an Ultra Z. That's an AVNet-based open source circuit board which has a management functionality on it. And the guys have ported OpenBMC to this device, which has a Xilinx Zinc on it, which enables management of all 16 nodes. You can find more about that on GitHub because of OpenBMC, of course, part of the Linux Foundation license. We've returned our changes to GitHub. So we've got these 2 megawatt boxes with smaller boxes that are hundreds of kilowatts, and inside of that, smaller boxes that are 3 to 4 kilowatts each. Liquid cooling that is the only way we're going to achieve it, because the sheer power density would not enable us to do this by air. And liquid cooling that brings about some challenges because it's very, very dense. To truly scale, we need zero airflow. Having some airflow simply is going to ruin what we've built in terms of pushing this in nice and dense. And immersion tanks are space inefficient and can't handle as dense electronics. So the project used isotope technology using immersion without submersion. Try and think about this more like a dishwasher. All of the IT gets wetted, but nothing's swimming. Part of the liquid cooling objectives were to achieve ASHRAE W4 and W5 so that this supercomputer can be run without any chiller plant. And that obviously saves substantial cost and energy. Part of the European Union's ambition here is they might be able to get outlet coolant temperatures hot enough for heat reuse. And we look at IT, ultimately, it's 100% efficient at producing heat. And our compute is a byproduct of that. So if we can actually make it use some of that heat, then that's quite helpful. The coolant system used a coolant that was very, very low risk. So part of the philosophy here was minimize the volume of coolant so that you've got a small volume of coolant that can be a very exotic coolant, and thus reduce the risk as much as possible associated with things like serviceability, flammability, toxicity, etc. And the coolant is a liquid fluorinated plastic, so think of a Teflon that is liquid at room temperature and has a boiling point of say 170 degrees centigrade. That's the sort of material that's around. And that being a fully fluorinated material is very inert and has a very low dielectric constant. And of course, going back to our high-speed signals, if we have a high dielectric constant, then our power consumption for those signals and that data flying around is going to be large. Having a low dielectric constant is very important in this coolant. Attached to that in the example that we're installing in Desbury is a facility coolant system at the secondary circuit that's at sub-atmospheric pressure. This here is TED. That's a thermal proxy extra high density test unit, and it allows us to test 4 kilowatts in 10U, even though we don't have electronics at the moment that can go to 4 kilowatts in 10U. It has 16 little modules that simulate the daughter cards. Hopefully, with the tech gods willing, we can get TED up on the screen running. So within here, you'll see the liquid fluoroplastic being circulated around the unit. It fills up in these heat sink-like areas that actually help accumulate the coolant near the hot spots, and then it overflows and brushes along with the rest of the electronics. So all the electronics get wetted, but we have a small volume of coolant within the box. And that coolant is force circulated, it doesn't change phase, it doesn't boil, and it can achieve very, very high densities with still high temperatures. And with all of the components maintaining their allowable junction temperatures, this system achieved a 47 degree inlet and a 55 degree outlet at 3.2 kilowatts in a 10U box. And you'll see at the rear of the unit we have a number of small pumps connected to heat exchangers. The heat exchangers connected to the secondary circuit. I would emphasize this is a lab desktop unit rather than a production unit. So a number of the manufacturing methods are more akin to a desktop lab unit rather than a production system. To conclude my talk, I'm going to talk a little bit about the management and the management controller on the front, which is freely available. So part of managing this system, we need to look at having OpenBMC with a capability to manage 16 nodes and the switch, and also do a number of measurements of the liquid cooling system. Now, at the moment, what we did was we ported the Facebook OpenBMC to an open source board from Avnet known as a Micro Z board. They brought out a new, more powerful board called an Ultra Z board. It's also open source from Avnet. And we then installed FreeRTOS Linux on this system and ported OpenBMC with some modification to enable 16 nodes. If you go to GitHub, to the OpenC page, you'll find our branch there called HEXA. HE for helium, which comes from Facebook, and XA for exascale, that comes from the EuroEXA project. Still a work in progress, but we hope that this might be useful to some people. That's the end of my presentation. Thank you very much for listening. Please connect to me on LinkedIn by going to thecoolingguy.me, and I'm happy to take questions. Any questions, please? Yeah. With the questions, please wait for the microphone so that everything's recorded.
Hi, thank you. The liquid you're using, is the 3M Novak? Is
No.
this that stuff? No?
No. Our liquid's manufactured by a European chemical company called Solvay. And it's made in Milan, Italy.
But these liquids have a rather high global warming potential, as far as I know. So you keep them inside this box. And
Indeed. One of the things you have to think about when you're looking at GWP is as GWP when it's a gas. So if you've got something that's got a low boiling point and you're boiling it all the time, you're producing a lot of gas. In this case of this liquid, the boiling point is much higher than water. So you don't have so much of an issue with lots of gas. The other thing that's worth mentioning is if you have a liquid that has a low GWP, it's because it's chemically unstable and it will degrade over time. So you end up producing more of it, disposing of more of it. It doesn't become a sustainable supply chain. You got a material that's very inert. You'll naturally have a higher GWP, but with the correct management, going cradle to cradle, you only produce a smaller volume that then is continually reused and isn't exposed to the atmosphere and doesn't cause issues. And in this case, to reuse the coolant is a relatively simple process and can be reused indefinitely, which also helps lower the costs.
You're using a sealed system by
Yes.
doing this, right? So that's why you're saying you can reuse the liquid and you don't necessarily have to deal with, because if you would use it openly, right, they would still evaporate.
Yes.
But since you're not doing that, you don't.
If
you
you used
don't
it
have that
openly,
issue.
it would evaporate, although rather slowly. And one of the things here is that you could pop the lid of the unit and you can service it with very minimal evaporative loss. And in servicing the units inside, it can be something as simple as removing daughter card, shaking off the coolant and removing it.
Thank
And
you.
It's non-stick.
Perfect lead-in. What is the maintenance process required?
The maintenance process relating to, sorry.
Deployment of the pilot.
So we're expecting that the system will be deployed and maintained as you'd normally maintain IT. We're not expecting any substantial maintenance to the facility level coolant system within the first few years, and then subsequently conventional refreshes of facility level coolant. And in terms of the coolant within the servers, we're looking at a full lifetime of coolant within the servers with no servicing need within the servers. The only maintenance related issues would be if you get server nodes that fail, and then going to the servers themselves, removing the housing and servicing those individual nodes. And that could be done even with the coolant in the unit, wouldn't need to be removed and recharged. So it's quite service friendly. Any further questions?
So maybe I missed the beginning of the presentation about, so what is the target of the project? But for example, now you can buy a 120 kilowatt rack from Cray as a supercompute, which you can build with, let's say, 20, 30 racks within a container. So is the target for this project to make something similar which is cheaper, or?
The target for the project is to invest in engineering for exascale, and that engineering being not just about hardware and facility, but being all the way through to operating system, network, application, across the entire spectrum as a co-design project. So a lot of the compute infrastructure, for example, is FPGA based, and the applications are being rewritten for FPGA, so you have very efficient processing of the applications. And a large portion of that is supporting infrastructure for such a system with a lot of complexity. And one of the things with that systems have things like a single memory space for the whole system, a single address space across probably an exabyte of RAM, and that's going to be very latency sensitive, so it has to be very compact. And we expect as things progress, we'll probably even push the density higher as things enable us to do so. And one thing as a takeaway for everyone in the room is to think about, what does the future look like for you guys? At the moment, are you designing electronics that is constrained otherwise by thermal design? Perhaps if you were to design electronics that could be as dense as they could be and create a thermal problem for an organization like Isotope or one of the other cooling vendors here, you might find that you can make stuff that's a lot more efficient. And I wonder, hearing some of the talks we've heard where the interconnect is going to be of many, many megawatts and large percentages of the overall footprint, that if you made things denser, you might find an improvement of tens of % in your overall energy efficiency, not to mention considering things up the supply chain by having smaller motherboards and denser components. Food for thought. So by all means, create thermal problems for us.
Thanks a lot, Peter.
Thank you.